So this part of the course is part two, described as systems and processes. And basically what we're going to look at is we're going to look at terms and definitions related to the science of thermodynamics that we need to deeply understand before we can actually understand the other principles and the further chapters of the module. So I'd refer you to chapter 1 in Sengal and Bowles, Thermodynamics and Engineering Approach, for if you want a broader perspective on this part. So we're going to look at important terms like property, dimensions, and units, and clearly define what they mean. And we look at important properties like temperature, pressure, and specific volume, and why they're important to understand clearly in thermodynamic systems. And we look at other basic concepts such as system, state, equilibrium, process, and cycle, and clearly define them. And that will give us a fundamental knowledge that we can build upon in further chapters. So let's start with property. In thermodynamics, a property is described as a measurable characteristic of a system that defines the physical state and behavior. It's basically something that we measure. Examples would be mass, pressure, volume, temperature, energy, and viscosity, and so on. And these would be their symbols. There's a footnote at the end, and it just says that in scientific notation and typesetting, the convention is to italicize symbols representing variables and physical quantities such as these properties, while keeping the symbols for units and dimensions in regular upright text. So a property can be divided into two categories, intensive property or an extensive property. So what do we mean by that? An intensive property is independent of the total quantity of a substance. Pressure and temperature are examples of intensive properties, whereas an extensive property depends on the amount of the substance present. Mass and volume are examples of extensive properties. So let's look at the intensive. Let's say you have a swimming pool full of water and it measures 25 degrees, and you have a small beaker that's maybe 400 ml full of water and it measures 25 degrees. We can clearly see that temperature is independent of the quantity of the substance available, that you can have the two large volumes of water measuring the same temperature. And we can say the same for pressure. A very large container can be pressurized to the same extent that a very small container could be pressurized. However, if we look at mass and volume, here we have a beaker that's maybe a 500 ml beaker, let's say, and it's nearly full with water. And we have a 500 ml beaker that's nearly empty with water. And we can see clearly that influences the mass and the volume. So mass and volume are very much dependent upon the quantity of the substance. So that's the difference between what we describe as an intensive property and an extensive property. Many extensive properties have corresponding intensive properties. So what we do is we take the likes of volume and other properties that you may not have come across yet, but we will do, and we will explain them fully as we go through the course: internal energy, enthalpy, and entropy. And if we divide them by mass, we convert them into what we call specific volume, specific internal energy, specific enthalpy, and specific entropy. And those specific versions of those properties are now intensive properties. And we can see that volume, for example, specific volume is meters cubed per kilogram, and specific internal energy is joules per kilogram. So we've divided by kilogram to convert that extensive property into an intensive property. So why would we do that? Well, the reason why we do that comes down to a statement called the state postulate. The number of properties required to fix the state of a system is given by the state postulate. And the state postulate simply states The state of a simple compressible system is completely specified by two independent intensive properties. So if we take a thermodynamic system, let's say like a boiler or a turbine or a condenser or a pump, let's say the boiler, for example, and as the fluid comes into the boiler, at that point, if we know two independent properties, two independent intensive properties, we can fully define the state of the thermodynamic system at that point and calculate all of the other properties, either by looking at them up in tables or by using equations to calculate those other values. So pressure and temperature, we've already identified our intensive properties, and they are also independent. So we can raise the pressure and the temperature stay the same. We can raise the temperature and the pressure will stay the same. The only exception to that is when we're going through a phase change and water, let's say, is going from the liquid state to the vapor state. It undergoes what we call the latent heat of evaporation. All the energy goes in to turning the water into a vapor, and the pressure and temperature are constant at that point. So they're regarded as being dependent upon each other. But if we have two independent properties and they're also intensive, that they don't depend on the quantity of the substance, we can fully define the state of the thermodynamic system at that point. If we done that before the boiler, after the boiler, we can tell what's going on in the boiler, how much energy is being used to boil up the water, for example. So independent properties, I've just covered that there. You can vary one and the other one's not affected. So an example would be density and specific volume would be an example of dependent properties. So specific volume is the reciprocal or the inverse of density and vice versa. So as you change one, the other one changes. Properties can also be categorized as state and path properties. So let's say we have a piston cylinder device as illustrated down here, and it's going through a compression process, as it would do maybe in the internal combustion engine of a car during the compression process of the internal combustion engine of a car during the cycle. Let's say at this point here, this is what we call a state. We can tell the pressure, the specific volume, the temperature, and as the piston moves from this state to the other state, it goes through a process. And the route that it takes going from one state to another during that process is what we call a path. And the properties at each state are called state properties. Examples are temperature, pressure, volume, external energy. They don't really depend upon what goes on before and what goes on after. And they're called state properties. However, if we were to identify the equation of this line for this process path and integrate it between states 1 and states 2, we will get the area under that curve. And if we get the area under that curve, that will give us on a PV diagram, pressure against specific volume, it will give us the work done during that compression. So work, and the same can be shown for heat on what they call a TS diagram, temperature against entropy. So work and heat are what we call path-dependent properties. They're dependent upon this path here and the equation of this line, basically, and what happens between these two states. So temperature, pressure, volume, internal energy are state properties. They only really depend upon the particular point, whereas heat and work depend upon this path here. Now, to distinguish between the two when we're dealing with differential symbols, we have the italicized D for dealing with state properties, and they're called exact differentials. And then we have the delta symbol here when we're dealing with path properties, and they're called inexact differentials. So if you see in the maths, if you see those types of differential symbols and you're wondering why one is represented one way and one is represented another way, that's the reason why. A dimension now, so that's properties. Moving on to dimensions. Dimension described as a measurable extent of a particular kind, such as length, breadth, depth, or height. So it's a type of measurement that we put on a physical quantity, like mass and time, for example. So fundamental dimensions are length, mass, time, temperature, electrical current, and we can divide dimensions up into two types: fundamental dimensions and derived dimensions. So over here we have velocity, volume, density, energy, and force. And you can see velocity is basically derived from length divided by time. There might be a little bit of confusion about the symbols T. So time has the property symbol of small t, but the dimension symbol of large T. Temperature, however, has the property symbol of large T, capital T, but the dimension symbol of theta. Just in case you see a capital T cropping up in different places, that's the reason why. When we're dealing with dimensions, it's important that we have what we call dimensional homogeneity. Dimensional homogeneity is a concept in physics and engineering that states that both sides of an equation must have the same dimensions in units. This principle ensures that the equation is physically meaningful and consistent. So let's take the example of Newton's second law of motion: force equals mass by acceleration. If we look at the dimensions for force, it's mass by length divided by time squared. On the other side of the equation, we've got mass, and then we've got acceleration, which is length divided by time squared. So we put them on both sides of the equation, and you can see it's dimensionally consistent. So it has dimensional homogeneity. Now, if your equation does not have dimensional homogeneity, it's going to be wrong. If it does have dimensional homogeneity, it still could be wrong because the maths has to be right. And then units. A unit is described as a quantity chosen as a standard in terms of which other quantities may be expressed. Another way of describing it, it's the standard measurement used to quantify dimensions, basically how you measure those dimensions. Over time, there's been different unit systems devised, but the unit system that we use nowadays is called the SI unit system. SI means System Internationale, French expression meaning international system of units. So it's the established unit system used in most countries around the world. So for mass, for example, we have the kilogram. For pressure, we have Pascal, volume, meters cubed, temperature, Kelvin, energy, joule, and so on. As well as having dimensional homogeneity, we also have to have consistency in our equations with the units. So we know density equals mass over volume. Just transpose that and get mass equals density by volume. So mass is expressed by the kilogram. Density is kilogram per meters cubed, and volume is meters cubed. The meters cubed cancel, and you have kilogram equals kilogram in this equation. So the units are consistent. Force equals mass by acceleration. So force is kilogram, the base units are kilogram meter per second squared, and mass is kilogram, and acceleration is meter per second squared. So you can see that the units are consistent in this case as well. Now, to check for consistency, the SI units may have to be reduced down to their base units. And what that means is the SI unit for the Pascal, the unit of pressure, for example, is defined as 1 Newton per square meter. But 1 Newton is defined as 1 kilogram meter per second squared. So when we put that in for the Newton, we can see that the equation, the units are expressed like this. we can cancel one of the m's there, one of the masses, and the Pascal equals kilogram per meter per second squared. And when we're dealing with work, energy, and heat, they all have the same unit, SI unit, which is the joule, but the joule's base unit is kilogram meter squared per second squared. So sometimes you're going to have to break down the unit, the joule, the Pascal, or the Newton, and other SI units as well, down to their base units to just make sure that your equations are consistent. So just to summarize this section, property, it's the characteristic being measured like mass, temperature, and time. It's basically what you're measuring. Dimension, the type of property described in fundamental terms. It's length, it's mass, it's t for time. So it's type of measurement that you're making on that property. And then the units, the standard measurement used to quantify dimensions, basically how you're measuring those dimensions. In a thermodynamic system, as we mentioned previously, it's if we know two properties that are independent of each other and they're also independent of the quantity of the substance, we can fully define the thermodynamic system at that point. And two easily obtained properties like that are temperature and pressure. So they're very important in thermodynamics sense, and they're also very important to clearly understand what we mean by temperature and pressure. So what I want to do now is go and define temperature and pressure in this section. So we'll start with the Fahrenheit scale. So I mentioned previously that the Fahrenheit scale was devised by Daniel Gabriel Fahrenheit, and he set zero reference at the temperature of ammonium chloride and salt water, I think it was. And that was the very first temperature scale. But then we moved on to Andreas Celsius, who is a Swedish astronomer, and he more logically set zero at the freezing point for water and 100 degrees at the boiling point for water. But then Lord Kelvin set up the zero reference, came up with the Kelvin scale. He was Lord Kelvin was from Belfast, I think, and he set the zero reference at absolute zero, the coldest temperature that can be achieved. And but 1 degree change in Kelvin was equal to 1 degree change in Celsius. And then the Rankine scale was devised by William Rankine, and he had also set zero at absolute zero, and 1 degree change equivalent to 1 degree change in Fahrenheit. So the Celsius scale is used in general use. In this part of the world, the Fahrenheit scale would often be referenced in America. If you're watching the Weather Channel over there, they mention the Fahrenheit scale. The Kelvin scale is the SI unit for temperature, because if we reference absolute zero, it's got more accuracy. And then if you're dealing with Fahrenheit in a scientific sense, then the scientific reference there would be the Rankine scale. So what do we mean by temperature? So a few definitions here. Temperature is a measure of the average kinetic energy of the particles in a substance. It's a property that quantifies kinetic energy of molecules, including their vibration, rotation, translation. Temperature is the measure of the warmth or coldness of an object or material, and it is an expression of thermal energy. So one way of thinking about it is if you have a glass of water and you zoom in on the atoms and molecules in the water, you'll see that they're rotating, vibrating, and moving around. And if you heat up the water, you'll see that they rotate, vibrate, and move around even more. And that's their kinetic energy increasing. Conversely, if you cool it down, you'll notice that the atoms and molecules are moving around less, and they've less kinetic activity, to the extent that if you cool the atoms of the substance down, the water down, until there's no activity in the molecules, no kinetic energy, and that they're perfectly still, you've reached absolute zero. And absolute zero is theoretical. It's a temperature that we haven't been able to actually achieve. The coldest temperature that we can achieve, that we've identified in the universe, is a place called the Boomerang Nebula, 5,000 years away from Earth. It measures 1 degree Kelvin, or minus 272.15 degrees Celsius. Although scientists have managed to use lasers pointed at atoms, I think, of silicon to try and immobilize them, and brought their temperature down to about 500 nano Kelvin, which is very close to absolute zero, but for all intents and purposes, and technically speaking, it's still not absolute zero. And the reason why we can't achieve it is because the colder it goes, and the more you try and still those atoms and molecules, the universe just wants to flood energy back in there and heat it back up, and it becomes a real technical challenge to try and reach absolute zero. So temperature is really a reflection of that activity that's going on in the substance. The zeroth law of thermodynamics, we mentioned that previously. It simply states that if two bodies are in thermal equilibrium with a third body, they're also in thermal equilibrium with each other. So if A is at the same temperature as C, A is at the same temperature B, B and C are at the same temperature. So we could replace A with a thermometer, calibrate it against B, and then go and measure object C and see what it measures. Different temperature measuring devices. You get the mercury thermometer, once again devised by Fahrenheit, used in traditional clinical and lab settings, measures temperature based on the expansion of mercury in a glass tube. You've got thermocouples used in industrial processes, scientific research consisting of two dissimilar metal wires joined at one end. A voltage is generated related to temperature difference. So this end, they would be joined. This is a protective sheet just to protect the wires from harsh environments. And then this end is connected to maybe an analog to digital converter, and you'll get your reading temperature reading taken into your PC. And then thermistors, combination of thermometer and resistor, used in medical devices, household appliances, semiconductor devices that change resistance with temperature change. So basically, they'd be on circuit boards, the motherboard of your PC, for example, telling the fan to switch on, or telling the system that the temperature is too high and it might need to shut down. Infrared thermometer. Infrared thermometer is a device designed to measure the temperature of an object's surface without making physical contact. They are widely used in various applications due to their non-contact nature, speed, and convenience. So let's say you have anything that's above absolute zero, which is everything, gives off radiation. And these systems can pick that radiation up, and it's calibrated to reflect the temperature of the object. So you can use them for non-contact measurements. It could be a pipeline that's very high up and it doesn't have a temperature sensing device, but you reckon there's some kind of issue up there, so you can point it up and see if is the system overheating at that point. Thermal imaging cameras, also known as thermography, is a technology that uses infrared radiation to create images that represent the temperature distribution of objects or environments. This method allows for the visualization of temperature variations across a surface, enabling the detection of hot spots, cold spots, thermal patterns that are visible to the naked eye. So if you wanted to get a building's energy rating value on your house, the people might use thermal imaging system and look at your house like this. And for example, you can see that the roof must be well insulated because it's not leaking any energy. but the gable end here is releasing a lot of energy coming out of the house. So you might need to insulate your house to improve your building's energy rating value. And then you can repeat the thermal imaging process afterwards and see does it improve it. This is called a constant volume gas thermometer. It's primarily used for precise measurements of temperature in scientific experiments and research. It is considered one of the most accurate types of thermometers because it relies on the ideal gas law, which has a well understood and predictable relationship between pressure, volume, and temperature, often used as a standard for calibrating other thermometers. Vessel filled with gas at low pressure, the temperature of the gas is proportional to the pressure at constant volume. So often used to calibrate thermometers because it's quite highly sensitive. So we'll move on to pressure. Pressure is the other property that's easily obtained in a thermodynamic system, and we'll show some devices that we use to measure pressure. But let's define what we mean by pressure. Pressure is defined as force over area and measured in pascals. So let's say if this piston cylinder arrangement here, you put a weight on the piston and the piston starts to bear down on the fluid inside. So it's the force acting down over the area here is going to determine the pressure that's being transmitted to the fluid in here, which acts on all the individual particles of the fluid and is transmitted to the walls of the container and acts perpendicular to the walls of the container. The Pascal is the SI unit for pressure. 1 Pascal equals 1 Newton per meter squared. But there are other units. So the bar, for example, is 10 to the 5 Pascal, which equals 100 kilopascal or 0.1 megapascal. The PSI, pounds per square inch, is often used as well, and it equals 6894.76 pascals. And then 1 atmosphere is approximately, which is the atmospheric pressure around us, approximately 101.325 kilopascals or 1.01325 bar or 14.7 psi. So it's important to be able to convert from one form to another because you will see pressure being expressed in different ways. So as I mentioned, at the surface of the container, the pressure force acts perpendicular to the surface. So we know that the pressure force acts perpendicular to the surfaces. However, we describe pressure as a scalar quantity, not a vector quantity. It has a magnitude, but not necessarily a direction associated to it. That's because we assume that it's acting perpendicular, whereas force can be acting in any different direction. And that's why we describe it as a vector quantity, as a force has a magnitude and a direction, but a pressure, we just consider it a scalar quantity with just the magnitude. Another type of pressure is the pressure exerted by a liquid, and it's called hydrostatic pressure. It's the pressure that is exerted by a fluid at a given point within the fluid due to the force of gravity. Hydrostatic pressure increases in proportion to the depth measured from the surface because of the increasing weight of fluid exerting downwards from above. You dive into the sea, immediately there's a pressure around you. The deeper you go, the hydrostatic pressure increases. It'll get to a point where you'll need a protective suit to protect you from that pressure or a protective vessel because the forces will be too high. It's the reason why dams are thicker at the base than they are at the top to withstand those hydrostatic pressure forces. And we calculate it by multiplying the density of the fluid by the acceleration due to gravity by z, which is the distance down to the point that we're measuring. The units are pascals or newtons per meter squared. Pascal is named after a French scientist called Blaise Pascal, and he came up with what's called Pascal's paradox. If you have number of vessels of different configurations filled up to the same level with the same substance, like water, for example, then the pressure at the base will be the same. Why? It's because they're independent of the volume um, that's involved. We look at the equation. If they're all water, then they all have the same density. So we can drop that. The acceleration due to gravity is a constant. We can drop that. And the pressure is related to the depth. And the depth is the same. So the pressure will be the same at the top. Sorry, at the base. And another type of pressure that we deal with in thermodynamics is the pressure exerted by a gas. If we have a container and there's gas in there, pressurized gas, there's a lot going on. There's a lot of molecules, a lot of atoms, a lot of rotation, vibration, moving around, collisions, and so on. And to try and mathematically model that would be extremely difficult. So what we do when we're dealing with pressurized gases is we apply the kinetic theory of gases and simplify the analysis. So there's lots of simplifying assumptions that we make. So for example, pressure arises from the collision of gas particles within the wall of a container. When a gas particle collides with a surface, it exerts a force perpendicular to that surface. Understanding pressure of a gas involves considering the kinetic theory of gas and the behavior of particles within the system. Excuse me. The kinetic theory of gases is a model that explains the behavior of gases in terms of the motion of the individual molecules. This theory makes several key assumptions. It treats a gas as consisting of a large number of tiny particles, molecules, or atoms that are in constant random motion. The volume of the individual gas molecules is negligible. Particles are considered to be point masses with no significant volume. The average kinetic energy of the gas molecules is directly proportional to absolute temperature of the gas, and it treats the collisions as perfectly elastic. So they're just some of the examples of the assumptions that we make when we're dealing with gas molecules. And they're covered under the kinetic theory of gases. And they play a crucial role in forming what we call the ideal gas laws that help us calculate the properties of a gas as it undergoes a thermodynamic process. So there are different ways we can measure pressure in thermodynamic systems. One simple way is by using pressure gauges. They look like this, but their working principles are kind of outlined in these two illustrations here. So pressure gauges display pressure values instantly, making them useful in situations where a prompt and straightforward reading of a gauge pressure is crucial. They can be installed anywhere in the machine where you need to keep an eye on pressure variations. So as the system pressurizes, the pressure comes up this tube here. It's called a board-on tube, and tries to straighten out the tube. And as the tube tries to straighten out, the linkage moves and the dial moves accordingly to represent the pressure. Widely used for their durability and accuracy, they measure pressure by the deformation of a curved tube. And the other example is a diaphragm gauge, suitable for low pressure measurements. They use a diaphragm that deflects under pressure. So the pressure in the system is exerted this way as well onto a diaphragm, and the diaphragm is linked to this linkage system, and that moves the dial accordingly to reflect the pressure. Obviously, with the diaphragm system, it's more sensitive, so you'd have to deal, as it says there, with lower pressures. You also have pressure transducers, which are basically screwed onto the system. The hole might be tapped into a pipeline, for example, and screwed in there. And then it may not give a reading directly on the pressure transducer itself, but the signal will be electrically transmitted through a control panel. And on the control panel, it might be displayed, the pressure value might be displayed, or it might be used to open and close valves in the system to provide a bit of control on the system. So pressure transducers measure the pressure of a fluid. These devices effectively convert the complex language of pressure changes into an understandable electrical signal, connecting the machinery with automation and control systems. Most pressure transducers use sensing elements that deform under pressure changes. Common types include strain gauges, capacitive elements, piezoelectric materials, and bonded foil strain gauges. Pressure gauges can come in two forms. One type of pressure gauge is simply just called a pressure gauge, and its zero reference is set at atmospheric pressure. And the other type of pressure gauge is called an absolute pressure gauge, and its zero reference is set at absolute zero. So what's the difference there? If you can imagine there's a pressure around you in a room, and it's atmospheric pressure, the pressure that's being exerted by the atmosphere. We measure it at approximately one bar or 100 kilopascals, or approximately 14.7 pounds per square inch. But as you go up, let's say a mountain, the pressure starts to decrease until you get into space where it's nearly zero. You'd have to go into deep space for it to be anywhere near absolute zero. Absolute zero, like absolute zero in temperature terms, is theoretical because we haven't been able to achieve it. We get quite close in high vacuum systems here on Earth. Basically, any pressure that's below atmospheric pressure is regarded as a vacuum. And we're basically pulling any air or gas molecules out of there to get rid of them all to reach absolute zero. But it's very, very difficult to reach absolute zero. And so far has been proved to be impossible. So it says here, select the appropriate pressure reference, gauge or absolute. It's crucial for accurate pressure measurements. And that an incorrect choice may result in errors of around 1 bar, especially for low range devices. Absolute pressure, the actual pressure at a given position relative to absolute vacuum, i.e. absolute zero pressure. Negative absolute pressures do not exist, so that's the lowest we can go. When dealing with pressures that need to be measured independently of atmospheric pressure variations, such as scientific experiments where the precision and consistency are crucial. So we use absolute pressure gauges when we want higher accuracy. Gauge pressure, difference between the absolute pressure and the local atmospheric pressure. Atmospheric pressure is the force exerted by the weight of the Earth's atmosphere at a given area. The standard atmospheric pressure at sea level is defined as 101.325 kilopascals. Most pressure measuring devices are calibrated to read zero in the atmosphere. Negative gauge pressures can exist, and this is called vacuum pressure, used in most everyday applications, such as measuring tire pressure, blood pressure, and so on. So let's say here we have absolute pressure here, and we have the atmospheric pressure that might be in a system that's not really pressurized yet. We put a normal pressure gauge on it, and it will read anything above atmospheric pressure. So as the system starts to increase in pressure, we get that gauge pressure and add it to atmospheric pressure, and the total will give us the absolute pressure in the system. When we're dealing with vacuum, so we have atmospheric pressure, and anything we pull below that is what we call a vacuum. So in vacuum terms, absolute pressure is atmospheric pressure minus vacuum pressure that we read on the vacuum gauge. A couple of examples here. Calculate the absolute pressure given a gauge pressure of 300 kilopascals and an atmospheric pressure of 101.3 kilopascals. Simply add the two of them together. Second example, calculate absolute pressure given a vacuum pressure of minus 50 and an atmospheric pressure of 101. So we take the vacuum pressure away from the atmospheric pressure, get the absolute pressure in that terms. If you've got a football, for example, the pressure inside the football is going to be atmospheric pressure. Same on the pressure on the inside of the ball, on the outside of the ball. But then as we pump it up, you're going to measure gauge pressure on the gauge. But if you wanted the absolute pressure in the ball, add atmospheric pressure to that to get the absolute pressure. I think generally soccer balls are pressurized up to about one bar gauge. And then in a vacuum system, it's going to be atmospheric pressure in here when we put the lid on it. And then as we start to pull a vacuum and take the air out of that system, the absolute pressure in that terms is the atmospheric pressure minus that vacuum that we read on the gauge. So that's pressure and temperature clearly defined. When we move on to talk about property diagrams, and a lot of the property diagrams present pressure against temperature, pressure against specific volume, temperature against specific volume, for example. So we need to clearly define what we mean by specific volume. And specific volume is basically the inverse of density. So we'll start with density. Density is essentially a measurement of how tightly matter is packed together. Density is also central to determining whether something will float when placed on the surface of a fluid. In general, density can be changed by changing either the pressure or the temperature. So increasing the pressure always increases the density of a material. So if you have a material and you squash it together like a sponge, for example, you're increasing the density of it. Increasing the temperature generally decreases the density. So maybe if you heat something up, it starts to thermally expand. So it becomes less dense. And density is an intensive property. So density, how much mass there is per volume, mass divided by volume, and in kilograms per meter squared. And specific volume, how much volume there is per unit mass, and it's volume divided by mass, or 1 over density in meters cubed per kilogram. If you were to take 1 millimeter cubed of air and zoom in on it at atmospheric pressure and 20 degrees, let's say, you would see that it's full of molecules, and it's estimated that there's 3 by 10 to the power 16 molecules for every millimeter cubed of air. So each molecule has a position and a velocity and a vibration. That's a lot of information. The microscopic positions and velocities are generally not useful for determining how macroscopic large systems will act. So we don't need to mathematically model everything that's going on in that 1 millimeter cube of air. What we do instead is take a classical thermodynamic approach and assume that matter is a continuum, is that it's made up of a matter where there's no gaps and no individual particles. So it says here, matter is made up of atoms that are widely spaced in a gas phase, but it's convenient to disregard the nature of atoms and consider them as continuous homogeneous matter, no holes or spaces between them. That is what we refer to as a continuum. The continuum approach allows us to treat properties as point functions. In classical thermodynamics, a macroscopic approach is taken that does not require the knowledge of behavior of individual particles. This allows for the use of mathematical equations to describe the behavior of fluids and solids on a macroscopic scale without having to account for the behavior of individual molecules or atoms. The other form of thermodynamics is called statistical thermodynamics, and it tries to analyze things on a molecular level by using statistics, and it would be used in molecular biology and trying to analyze chemical reactions and things like that. But that's not the concern for the type of thermodynamics that we're doing from an engineering point of view. And the type of thermodynamics that we do is called classical thermodynamics. And you might hear continuum being mentioned as a word, and that's what it means. Thermodynamic system. So thermodynamic system is defined as a quantity of matter or region of space chosen for study. A system or region in space is surrounded by a boundary that may be real, the wall of a cylinder, or imaginary, in other words, the nozzle outlet. The boundary can be fixed or movable. Ideal boundary has zero thickness, has zero mass, and does not occupy any volume in space. Choice of a boundary is somewhat arbitrary, as it depends on what you want to study. And the area beyond the boundary is called its surroundings. So we may not want to analyze the whole thermodynamic system. So we need to specify what part of the system we're trying to analyze. So we draw a boundary around it. We don't want to mathematically take into consideration the boundary. So we just assume it has zero thickness and zero mass and does not occupy any particular volume. So this is an example here, theoretically, of a system. And outside the boundary, which is defined by this dotted line, is the surroundings. In a more practical term, if this was a nozzle that's used to increase the velocity of a fluid going through a pipeline, the real boundaries are the nozzle sides here. And then we imagine a boundary at the beginning and the outlet here. And we apply our theoretical apply our theory to that, to just the nozzle, and then find out what's going on there. Now, boundaries can move. So in this piston cylinder device here, as the gas expands, as we heat it up, the piston might rise, and as it does, the boundary will move with it. So it can move as well. It can be moving boundary system. Thermodynamic systems can be open, closed, or isolated. So it says here an open system or control volume that it's often referred to. If there's an open system, if there is a transfer of mass across the boundary. So the example here would be in this container. We've got water in there, we heat it up, and if the water, which we regard as the mass or the working fluid, if the vapor leaves the container, which is the system, the thermodynamic system, then it's crossing the boundary. So that's an open system. Here with this vessel, what we've done is we've capped it. So although we heat the water up, it cannot leave. So that's regarded as a closed system because the matter or the working fluid cannot leave the boundary. And then an isolated system is where we cap it once again, but we also insulate it so that there's no heat transfer. So there's no energy crossing the boundary in any form. Examples of open systems. So open system or control volume, as it's also known, is a system in which the transfer of mass as well as energy can take place across its boundary. And one example would be boiling water in a pot. What you have there is you've got heat crossing the boundary, and you've steam, which is the mass being turned into steam, crossing the boundary as well. In industrial boiler, water entering, being heated up and going out as steam. Again, open system. Heat exchanger, you have water coming in and going out, but it's going out warmer because it's taking energy from another fluid system, and it goes out. So heat is crossing the boundary, and there's a mass flow taking energy with it going across the boundary. And then another example, steam coming into a turbine, rotating the blades. This time there's a mass flow of energy coming in the working fluid in the form of steam, but the other form of energy that's leaving the system, in this case, is work going out from the turbine, mechanical work. A closed system, a system in which the transfer of energy, heat or work takes place, but no transfer of mass. For example, water heated in a closed vessel. So this time with the pot, we put a lid on it, and the water can't leave in the form of steam. So it's a closed system. a piston cylinder device. When we compress it, the pressure will increase, but and there may be a release of heat from the system, but there will be no mass transfer. The gas inside there will not leave the system. So it's a closed system. And although those pistons can expand and contract, they're still closed, but the boundary may move with it. So it's a moving boundary system as well. And then finally, you've got the isolated system. And the best example there, where there's neither transfer of the working fluid or the mass from the system. There's also no transfer of energy takes place across its boundary. And the example would be a thermos flask. Hot water, coffee, or tea kept in the thermos while the lid is closed. So what I want to do now is describe thermodynamic state and equilibrium. In thermodynamics, a state refers to the condition of a system as described by its properties, such as pressure, temperature, and specific volume. The state of a thermodynamic system is fully defined when these properties are specified. Understanding the concept of a thermodynamic state is fundamental for analyzing and predicting the behavior of systems in equilibrium and non-equilibrium positions. So let's take a very simple thermodynamic process of a piston being compressed from one point to another, compressing a gas in there. At this point, we call this a thermodynamic state. And we would be able to measure the pressure, the temperature, and the specific volume, let's say, at that state. And as the system compresses, it goes from one state to another. And the route it takes is called a process. And this is the process path. And when we reach the second state there, the pressure, temperature, and specific volume may change. But that's what we refer to as a state. In fact, the system is undergoing a series of change of states as it goes from one point to another. So at any point, we could stop the system and theoretically calculate the pressure, the temperature, and specific volume. Now, the reality is that these pistons reciprocate back and forward very, very fast. So do we actually know the pressure, the temperature, and the volume, specific volume at any particular point? The reality is at any particular point, the pressure and the temperature there might be a range of pressures and temperatures in the gas at any particular point in reality, because they can reciprocate a few thousand times per minute. But what we assume for the theory is that the piston is actually moving slow enough that at any particular point, the system is in equilibrium and we can measure the pressure, the temperature, and the volume. And theoretically, for let's say an engine idling at the lowest speed, if we apply the theory taking the equilibrium approach, then they approximate to each other. So the maths actually make sense. These systems are usually called quasi-equilibrium. Quasi means as if in equilibrium, as if it's going slow enough so the pressure and the temperature is at a particular value at any particular point. A more advanced form of thermodynamics is called non-equilibrium thermodynamics. Focuses on systems where gradients of temperature, pressure, chemical potential, and other properties drive continuous change. So process and a cycle. Process, as I mentioned, so we go from one state to another during this process, and the path or the route that it takes is called a process path. And so a process is defined as any change that a system undergoes from one equilibrium state to another. And the path is the series of states through which the system passes during a process. The process description includes initial and final state, path of the process, and interactions with the surroundings. There are a number of standard processes that occur often enough in reality that they're useful to try and help us understand the theory. And some of those processes that happen often enough are outlined here. You've got isothermal process, a process that exists or occurs at constant temperature. You'd have a straight line like this on a temperature against specific volume diagram. Isobaric process, and this is one that occurs at constant pressure. So you'd have a straight line at constant pressure on a PV diagram. And then the isochoric or isometric is one that occurs at constant volume. So you'd have a straight line when on a PV diagram that plots pressure against specific volume. So what we do is we combine a lot of those processes and produce what we call thermodynamic cycles. So here we see the internal combustion engine of a car. It's going through a compression, ignition or combustion, and then there's an expansion and an exhaust cycle. So we can see that here in what we call the Otto cycle. We've got the compression, then there's an ignition, and then there's a power stroke, and then there's an exhaust stroke as well. And the Otto cycle describes how the cycle of a petrol engine, thermodynamic cycle of a petrol engine. Over here we have the diesel cycle that describes the thermodynamic cycle of a diesel engine, and here we have the Rankine cycle that describes the thermodynamic cycle that a power plant would undergo. Another one is the vapor compression cycle used in refrigeration, and then the Carnot cycle, which looks like this and is a way of describing an ideal cycle for a power plant, for example, for a heat engine. And the reversed Carnot cycle describes the ideal cycle for a refrigerator system. And final slide, you'll also hear the term steady flow process. So a steady flow process is a concept in thermodynamics, often associated with systems where fluid, in other words, gas or liquid, flows continuously through an open system or control volume, e.g. a section of a pipe. Examples would be pumps, turbines, boilers, condensers, power plants, and refrigerators. In a steady flow process, the fluid properties at any given point within the control volume do not change with time, meaning that the mass flow rate, energy flow rate, and other properties remain constant over time. The term implies no change with time. The opposite of steady is unsteady or transient. So we have a turbine here. It's an open system, the steam coming in and going out, and we assume the mass flow rate of the steam coming in and going out is constant and doesn't vary. And we can analyze this as what we call a steady flow process. And we will be looking at these later on in the course.